Section 6.7, the remainder theorem. In these examples, we have two methods that we actually can use to solve the given problem. In this first example, we're given a function, and they're asking us to evaluate the function when x is a -2. So what that means is everywhere there's an x, we can replace it with the given value and then simplify the expression. So everywhere there's an x, I will put a -2. Following the order of operations, then, we can simplify it. Exponents -2 to the fourth power is 16. -2 to the third power, -2 times -2 times -2 is a -8. And then we're down to our multiplication. I'll take care of the multiplication here while I'm rewriting it. We have a -4 and the +1. So back to simplify these multiplication problems here, we have 6 times 16, which is a 96. A negative times a negative is positive 24. Plus we have the -4 and we have the +1. If we add left to right, then a 96 plus 24 is 120. In place of those two, then adding the -4 to that, or subtracting 4, we now have a 116, and we still have a +1 to add on, which gives us a final value of 117. Well, instead of this method, we could apply something called the remainder theorem. When a polynomial function is divided by something of the form x minus a, the remainder is related to the function value f of a. And that may sound like quite a complication. And let me read the formal theorem here. The remainder theorem states the remainder obtained by dividing the polynomial function by x minus r is the same as evaluating the function at r. So let me show you how the remainder theorem works for this problem. I'm going to use synthetic division and divide this polynomial by the value that we want to evaluate it. So I'm going to put a -2 as my a value from synthetic division, x minus a -2, putting our coefficients from our polynomial that we're dividing, decreasing power. So we have a 4, 3, we don't have an x to the second power, we will put a placeholder of 0, our 2, which is x to the first, and then our constant term. So we have a 6, a -3, 0 for our x squared, 2, and 1. Synthetic division wise, we bring down the leading coefficient, we multiply by our value of our a, which gives us a -12. We'll add then -3 plus -12 is -15. We go back and multiply. Negative times a negative is positive. 15 times 2 is 30. We add, that's 30. We multiply. Negative times a positive, 30 times 2 is 60. We add 2 and -60 is a -58. We multiply, a negative times a negative is positive. 58 times 2 turns out to be 2 times 8 is 16, carry the 1. 2 times 5 is 10, with that carried is 116. And here's our 117. If you recall from synthetic division, this last value is our remainder. And from the remainder theorem, it also is the value of the function when you evaluate it at that value of your divisor. So here I showed plugging in the value. Our solution was 117. I also got the value by doing synthetic division and looking at the remainder, which is supported by the remainder theorem. So I have another problem. I want to know the value of this function when x is 3. You have two options. You have method 1, which is to replace x with 3 and simplify the value, which 3 to the third power. 3 times 3 times 3 is 27. 3, or try it again, 2 times 27 is a 54. Minus 3 would be a 51, plus the 4 is 55. That one wasn't too bad as far as evaluating. That last one, synthetic division, definitely in terms of time was a time saver. But let me illustrate using synthetic division for our second option. I want to know the value of this function when the variable is 3. I will put 3 in the box for synthetic division, making sure that we put placeholders for powers that are missing on our variable. We have a 2x to the third power. We do not have an x squared, so I'll put a 0. We have an x to the first power, and the coefficient is a -1, and then our constant term is 4. In synthetic division, we bring down the first term. We multiply, placing it underneath the second coefficient. We add those two values together. Back for a multiplication, 3 times 6 is 18. -1 and 18 is 17. Back for multiplication, 17 times 3 is 51, and add is 55. The answer to the problem is the value of our remainder, which is always the last number in our what we call the depressed equation. So G of 3 is 55 from synthetic division or evaluating it by replacing the variable.